Oh, ready? Okay, hello everybody. Thanks for coming here. First of all, I'm using a microphone for the streaming. It's not that my voice is very low, but it's just for streaming purposes. So also in the part of questions, I would appreciate if you also use a microphone if you want to ask a question. So welcome to this year's seminar for the Research Unit 3 of the Bolin Centre. This is the unit that studies water resources, hydrology, permafrost, and the cryosphere. We have one invited lecture per year, and this year we decided that Wang Erlandsson from Stockholm Resilience Center would be the perfect candidate. So we welcome you, Lan. Thank you for being here. Lan is a researcher in Stockholm Resilience Center. She works with moisture recycling, water governance, and freshwater planetary boundaries. She was also last week doing a presentation in the Water Day in the Swedish Academy of Sciences. So thanks for being here. Lan will talk today for 45 minutes, around 45 minutes, and then we will have 15 minutes for questions. And you can also stay afterward because I think we're gonna have a small coffee. I don't know how the coffee will work out, but and then there's another seminar coming on, also sponsored by the Bolin, on how to write applications and articles. So, okay, so Lan, welcome, and please proceed.
Thank you so much, Fernando, and thank you so much for inviting me to talk here. I'm very excited and honored. So today's topic is terrestrial moisture cycling. It's what I've been working with since I started my PhD. So I also received important contributions from my supervisors, PhD time with Lina Gordon, Jan Rockström, and Hubert Savenay at Delft University of Technology in the Netherlands, and also from my academic brother. They share the same supervisors, so Ruud van der End and Patrick Keys. So first question that's really related to moisture cycling is, where does the rain come from? Do you have an idea? Would you have a guess? Does it come from land mostly or ocean mostly? Just shout out. Yes. Ocean mostly. How much would you say? 3%, 30%, 60%, 80% maybe? Yeah. I think most people tend to think that the majority of the precipitation directly comes from the ocean, because whenever you look at the stereotype water cycle picture, you see this picture of the water flowing from the ocean and then falls down on land and then runs out again with the rivers. And that might be true in places like Sweden, where the moisture cycling is not very strong. But so let's look at a video of, this is a video showing the ratio. So on top, when it's red, it shows that a very high percentage, maybe up to, when it's really, really red, it's 100%. But most of the red is around 80, 90% of the moisture has a terrestrial origin. So it actually comes from land, where it's very red. And as you see, like countries like Sweden doesn't receive that much moisture from land, but in places like northern China, large parts of Eurasia, the Andes, South America, West Africa, Central Africa, and also large parts of North America actually receive a lot of its precipitation from land. And this is going from January to December. So now we're in July, you see that this high terrestrial moisture cycling ratio is moving up to the northern hemisphere, and then it moves down again, this reddish colorings. So maybe we don't need to go through all the video. You get the sense a little bit. And we can sum it up in a more conceptual figure. This is the evaporation coming from the ocean. Well, that's where it starts, but then it falls down as precipitation. And here it evaporates again. And oops, now I pressed the wrong button. Right. And then it gets transported and falls down in precipitation again. And so this evaporation over land that comes down as precipitation again. This cycle is what we term the terrestrial moisture recycling. If we summarize it over the mean over the whole year, we can see that the areas that really comes up are the areas that we also see in the moving video. And in northern China, it's actually really up to 80–90%, and also maybe 70% in the La Plata region and West Africa as well. And if we look at the reverse, so where does that evaporation come from? You sort of see how it follows the wind patterns from the Amazon down to the La Plata. So in the red, in the lower picture is showing in red a high percentage of evaporation that also goes to other land areas as rainfall or precipitation. So to get these nice videos and pictures, I didn't create a model, Ruud van der Ent did. As a master thesis, no pressure for any master students here. But so there are moisture tracking models out there since a long time that do sort of tracking of one place. That is very computational intensive, like Lagrangian model they're called, and you track the particles. So you also use them for tracking particles, not just moisture, but any pollution, airborne pollution. But this model is more, you use a water balance approach. So you divide the atmosphere. Originally, it was just one column, and you assume that the entire atmospheric column is well mixed. But in an update, it was divided in two columns. So by treating the atmospheric column and the water balance, and you have this input data from reanalysis data is called. So it's a numerical weather forecasting models and then using data assimilation. So you have the specific humidity, the winds for the entire atmospheric column. You have the precipitation, you have the evaporation. And the precipitation, you can use other precipitation source data that it may be better than reanalysis. And evaporation can also be used from hydrological model output. And so by joining those, so it's just not simulating precipitation, it's just tracking. Yes, so it is, I say evaporation because we use both evaporation from ocean and from land. And then my supervisor, Hubert Savanai, or my former principal, he's very wary of the term evapotranspiration. So he thinks we should use total evaporation because evapotranspiration comes from, yeah, okay, it's a long discussion, but I mean total evaporation, including everything, yes. So now that we know where the rain comes from, why is it useful, you think? I mean, if we look at the conceptual figure again, if it comes from land, it means that whatever we do on land also affects evaporation, and whatever we do that affects evaporation then might have a knock-on effect on rainfall and precipitation. So I will list 4 examples, 4 reasons for why we should care about this. One is because now we can show how remote land use change is affecting food production. Most of our food production, our rainfall agriculture, most of our agriculture is rain-fed. I think on aggregate is about 70%-ish. And in some areas like sub-Saharan Africa, where a lot of food security issues arise, actually 95% of that farmland is rain-fed. And it's 90% in Latin America, 75% in Near East and North Africa, 65%. So it's a very high percentage that relies on rainfall for food production. And so when we look at specific areas and for specific growing season, when we track back, so this is showing a specific region, the North China region, and we track back, where did the rain come from? It's spread out over a very large area. So in that yellow little one inside, that's the region that we study. And the bigger area, it shows the fractional contribution. So the darker, so it's sort of course, the closer the region you are, the more contribution you have. And here you can see that when it's black, it's a fractional evaporation. It's actually up to between 80 and 100%. And if we analyze the threats that exist in these regions. So there's a lot of deforestation threats, urbanization, salinization. They're all things that could change evaporation. But it also means that we can try to figure out what kind of opportunities do we have to deal with it. If we do afforestation, water harvesting, it also affects the evaporation and subsequent rainfall. And Western Sahel, a similar figure. Maybe I'll not deal with it, but it's a similar thinking. And we went through for all these regions. But it's not just our group that has done work on this. Others have also looked at these moisture recycling links. And when they look at certain bread baskets in terms of maize, soybean, wheat, and track it back, they see that they're very susceptible to moisture from land cover change. And they used a simple crop model and saw that the potential crop yield reduction was in the range of 1 to 70%, which is comparable to the consequences that we study in terms of CO2 impacts. So it's not entirely negligible. And when in our analysis, again, we also try to do a scenario analysis. So if we couple a hydrological model with the moisture tracking model and then see what happens if we deforest. So that sort of quantifies the role of the forest. We did it for Mato Grosso in South America and look at how that changes. This is a change in precipitation in this sinks area. And interestingly, this is from January to December over the year. And interestingly, you see that the wet grasses is the precipitation. So in blue, that's the current vegetation, and red, that's the desert one. And we see that maybe the most important here is not that the precipitation is reduced, but that the growing season, the dry season is vastly increased. So rather than going between maybe July and October, it's now maybe starting already the dry season in March because of this evaporation reduction in forest. And others have also done more earth systems, so much more complex analysis using earth system models. And they still show this effect that because of the climate feedback that you introduce, that leads to reduced precipitation. And when you expand agriculture into regions like the Amazon rainforest, you actually also reduce in rainforest to the extent that you actually reduce the yield. So it becomes a very self-defeating situation. So the more agriculture that expands, the less productive it becomes, was their conclusion. And then the second reason, so food, but also how it affects water resources. So if we look at the words megacities, where a lot of water supply issues arise, and a lot of the discussion is around how can we create water supply in terms of reservoirs, in terms of blue water supply. But then this is showing the watersheds of the megacities where they get their supply. And so we analyze the basins where these megacities receive their water and track using this precipitation shed thinking. So precipitation shed is, this is a more conceptual figure from what we earlier saw, where this you select a sink region and then you track back with the moisture tracking model and see where it comes from. So you could see it almost as an analog to watershed, with the difference that watershed has a hard boundary, whereas precipitation shed is more a gradual vanishing, gradual decrease. But so if we do this precipitation shed of a watershed, are still with me for all these 29 megacities, this is how it looks like, all these precipitation sheds in real and not in conceptual. You still see this gradual vanishing, and this is just examples. I'm not going into details, but from this analysis, we saw that 19 of 29 of the megacities that we analyzed, they depend for more than a third of the water supply on evaporation from land. And of course, moisture recycling is not the only factor that matters. So if we are thinking about the vulnerability of these megacities to moisture supply from land use change, also outside the immediate uptake basin, we look at, to start with, the moisture recycling related stuff in terms of how much of that moisture is vegetation regulated. So we do a land use change scenario, comparing the desert land or with the current land. And we look at the land use change, so how much potential land use change is taking place or has taken place. I think we did in this study. And then also in terms of what happens with interannual variability, because a lot of these cities or regions also appear to, so moisture recycling intensified during dry years. So the more dry, the more you need the rain, the more dependent it became on land areas for its supply, because a lot of these dry years is caused by a reduction in ocean influx. So the relative role of land becomes more important. So we call that dry year moisture recycling sensitivity. And then we pair it with economic capacity and water stress, and we come up with a vulnerability score. It's divided by this maximum of all megacities because it's more a ranking rather than an absolute number. It's also a equation we came up with, so don't take it too seriously. But anyway, it's just a way to identify cities that are relatively more vulnerable in terms of moisture recycling. And the ones that we found were most important are Karachi, Shanghai, Wuhan, and Chongqing. And you see that the Chinese cities come up a lot also because of the strong moisture recycling in that region. Reason 3, remote land use change affects river flows. So the common traditional way of doing it in hydrology is that when we look at how river flows are changed, we simply look at the land use change within that basin and assuming that all evaporation from the basin leaves the basin. That's our common assumption. But with moisture recycling, if you have a sufficiently big basin, and if you're in a region where moisture recycling is important, some of that evaporation comes back, and some of the land use change that happens outside the basin also influence the river flows within your basin. So I did a global land use change scenario with this coupled hydrological model with moisture recycling model. And this is showing all land use change that humans have made. So it's showing the pasture areas in yellow, the crop areas in red, dark orange. It's not very clear. And so against what we call a potential vegetation case. So what would the planet have looked like without humans, but given today's climate? So it's a hypothetical present day vegetation case. And if we feed this into the hydrological model, first we get an evaporation change in the upper, upper right corner for you. And you see that a lot of red, that's a reduction in evaporation due to deforestation, and a lot of blue, that's an increase due to irrigation. And you see in the precipitation change, that's when we run it also through the moisture recycling model, and you see that sort of this change is smoothed out, so you have a smoother gradient, but it's reflecting these changes. And then P minus E, we derive the river flow change for different basins in the world. If you sum that up over all global land aggregated, and you do not take the moisture recycling factor into account, that's what you get. Evaporation change, that's the reduction, that is directly corresponded by a river flow increase in the blue down there, no TMR, no terrestrial moisture recycling. But if you, and no changes in precipitation. But if we do take that into account, terrestrial moisture recycling, we see that evaporation increases a little bit more because we iterate the models until we see the full effect, because when you change evaporation, you change the precipitation again, and when you change precipitation, you change the water available for precipitation again. So that's why evaporation becomes a little bit larger. And then you have quite a substantial precipitation change. And the river flow change is not as much as you would have without taking moisture into account. So we could say that land use change reduces both evaporation and precipitation, and that moisture recycling is providing I was a bit hesitant, maybe buffer is not the right word, because it's not buffering extreme flooding anyway, but it reduces this mean annual river flow estimate. If we compare this to other studies that have been done without taking moisture recycling effect, and surprisingly, even given that we have quite complex climate models in place, there were even quite recent studies in high impact journals that just look at evaporation change and derive river flow change without any thinking of moisture recycling or land atmosphere processes. And so we see that in the middle line blue, and now this point when I should have a pointer, but in the middle river flow change by, and this is a blue line, and then you have this non-solid bars. It says no TMR. And it's quite comparable to the range of the different literature estimates. But then when we take moisture recycling account, you see that it's really in the lower range of those literature estimates. And so how does it look like then from moisture recycling perspective for a river basin? Conceptually, this is what you think. So without moisture recycling, you would not have the first two arrows. You would just have the export and the river flow change. But so when we take moisture recycling account, what we do is simply adding those two, precipitation entering the basin and the recycling within the basin. And so from the aggregated level, the bars that we looked at earlier, the change is quite corresponding to the, it was maybe about 40 to 50%. So it's quite close to the 40% of all precipitation that has a terrestrial origin. But locally, so like the Amazon, you see that the blue bar, the solid one, and the non-solid one, that's quite a big difference. So in Amazon Congo, you can get it more wrong than the mean aggregated global average. And let's look at a case in Yangtze River Basin. So these two upper ones are just the simple precipitation source, the precipitation shed, or the evaporation sink, so where the evaporation from the basin is going, so the evaporation shed. And if we look at the changes between the difference between the current and the potential vegetation case, this is what shows up. Blue is an increase, and red is a decrease in the precipitation source for Yangtze River Basin. And this is the corresponding one for evaporation shed. If we apply it to the more conceptual figure, this is the irrigation in India would be the inflowing arrow. This reddish reduction within the basin is what happens within the basin, and what's almost not visible, I think, with the light is what goes out from Yangtze Basin. And this raises question, of course, because when you ask anyone, is Yangtze a transboundary basin? Is it a national basin? Of course, it's entirely within the Chinese national border. But if we look at this map, and if I sum up the land use change influence, so this is very specific to this land use change scenarios that we applied. If we apply different land use scenarios, this pie chart will, of course, change. But still, it shows that China only had a 70% influence over the river flow changes within the basin. And by any standard, that would be called a transboundary river basin. So I think by taking moisture recycling into account, we really see that there's a large influence from outside the basin that we should consider, at least maybe not for all basins in the world, but for certain basins, certainly. And it's not just our analysis. I just want to throw out some other researchers who have done different methods. They use the Earth system, my general circulation model, together with land surface model with irrigation scheme in it. And they also found, even given that they have circulation changes in how it affects monsoon, they still find that you have both this these arrows are just showing the moisture flows in different seasons. So there's flow from irrigation that goes to Eastern Africa, up to 40%. They say, I think there is some noise and also the grid cell. So maybe it's not 30% over the entire area. So should be taking a little bit care, but still it's significant. And that's the irrigation in South Asia, also substantially influence the climate throughout Southeast Asia, China, through advection of water vapor and through altering the Asian monsoon. And reason number 4 is that moisture recycling is not only just this provisioning, it's also initiating feedback in ecosystems. So if we look at forest resilience literature, traditionally you have this tree cover on the vertical axis, you have the rainfall on the x-axis, and you'll see that the forest at some point, if the rainfall is reduced enough, will collapse into a savanna state. So you don't have this intermediate state that is stable. So you have 2 stable states, savanna and forest. And for the savanna state to recover to a forest state, you would normally need much more rainfall than originally needed to trigger the collapse. So this is called hysteresis. And moisture recycling is one major factor. You have other reasons as well, like fire and fragmentation and other ecosystem processes. But moisture recycling is one of those that helps the forest being stable state. But then if it collapses, you don't have the moisture recycling anymore, which makes it harder to recover. So it's one of those processes that keeps this hysteresis in place. And so when you this is just showing that the high resilience in the ball and classic ball curve figure that when moisture recycling disappears, when you deforest, you are sort of lifting the landscape, the stability landscape. You have a lower resilience and the ball more easily rolls over in terms of if you have a bad year with drought, the forest more easily tips over. And in a study using the moisture recycling flows. So now we have pre-processed all the moisture flows between grid cells in the South America. And then Bolin Centre was leading the study. And so she used a network analysis method. So treating the moisture flows as links and the grid cells as nodes. And so coupling a very simple hydrological model so that links whatever land use change you have is having a certain evaporation response property. And so when she did the experiment of cutting off moisture flows from the ocean or having deforestation analysis, and the precipitation start reducing because of this model in the network that so the forest could also fail. So it was 3 components: moisture recycling, forest resilience, and hydrological model. And so when the rainfall reduced, the forest couldn't keep up and transform into something treeless or savanna, and then in turn reduce evaporation. So you could see that along this chain of the moisture flows, that the forest loss was self-amplifying. And just the self-amplification effect was about 13% of the forest loss that was seen. So that's the foe, if you see deforestation as introducing this kind of feedback. But then other side, you could also see it's both a risk and opportunity thing. So if you look at the dry seasons or droughts, forest is also really important for providing evaporation through transpiring. So during the drought years, when you don't have maybe as much inception and as much ocean influx, this was a quite recent study. I also show his picture here because Ari is at Stockholm Resilience Centre for now. He's used to be at Wageningen, but he's here for this year. So if you want to talk to him, he's actually in person in Stockholm. And so he showed that transpiration was really an opportunity as well. So if you preserve the forest, you have an additional buffer in drought years. So if you manage the moisture cycling right, you can have great benefits too. But so this leads then up to the question, if there is so many reasons to care about where the rainfall comes from, it's providing food, it's providing water, it's I think influencing river flows, is influencing forest loss. So should we think about governing it? Because there's no governance around this at all. And if so, how? Well, sometimes it's also about speaking the language of policymakers when something is important. So I find it interesting that, so when we found that the UN water report caught up on our research on moisture recycling, they didn't use words like precipitation source. I mean, precipitation source region source has been used ages. I mean, moisture recycling studies in the Amazon, there were isotope studies of where the moisture came from in the 70s. So we've known for a long time that rainforests have this strong moisture recycling, using isotope studies or other moisture recycling models. But when Pat coined the word precipitation shed, it really caught because it had this analog with watershed, something that they could relate and understand. And they even call it atmospheric watershed. And I think I've heard other words like rainbow water out there, just putting colors. And yeah, I just found it interesting how these words really mattered. And then we also maybe more purposefully coined moisture recycling as an ecosystem service. So if we look at these two cases, a current vegetation and a desert land vegetation scenario, and compare the differences, that will effectively be what the vegetation is hypothetically, theoretically providing us. Of course, if you do this in a climate model, you will mess up the circulation entirely. But if you're just interested in the moisture recycling link, this is one way to just show where the vegetation is providing moisture. And you should see that it's quite similar to how the moisture recycling map looked like in the past, but now we can sort of quantify this is the ecosystem service of vegetation from a moisture recycling perspective. And so next step for us was also to then think of, given the interest, how can we then, if we would explore, how would governance look like? And would there be different types of moisture recycling regimes? So based on the ecosystem service analysis, so the difference between desert land and current land, so it's based on this map, we chose the regions that had most ecosystem service sort of, and did this sort of dependency wheel. So you have different countries. This is for South America. So you have Brazil, Uruguay, Paraguay, Bolivia, Argentina, other land and ocean. And this is just showing the moisture flows between these regions. And if we do it for all these 4 different regions, these dependency wheels, the wheel charts look very different. So North America is quite simple links. South America, a little bit more complex. Asia, more complex. And Sahel is just a lot of flows. And so we started thinking, so what kind of typology, if we simplify that in something conceptual, that could be discussed? So summarize it in type 1, exchange among small number of countries. Type 2, you have one nation providing to other countries, sort of a water tower thinking. Type 3, that is actually they have elements of it in all 3 regions. That's sort of a cascade through different nations. And type 4, that is just a network of exchange, just a mass. And maybe Sahel is more into this network than in the cascade. And there's maybe different proportion of elements and that can be found in both all typologies. But so, and then it becomes easier to discuss what kind of governance strategies would you fit to different kind of moisture flow types. So if you have a very simple moisture flows, you could think of something more causality based because it's easy to attribute who did the harm, who made the land use change that affect the rainfall. You could think of some ecosystem service payment. You could have a bilateral treaty like you would have in a transboundary river basin between few countries. But if it's really complex, maybe you have to have some more regional, multilateral agreements, or maybe even not that is possible, and you just have to think of changing the norms. And there's of course challenges related to this as well. So even if you would do a no harm, harm attribution, it's still difficult. So how do you set this threshold? You could look a little bit up at how transboundary river basins do it, but still it's even more diffuse. And also the scientific assessment method has to be considered legitimate by all parties involved, which might be too immature at this stage. And for very complex situations, it might be difficult to set goals because the goals are all different between the nations, and it's also difficult and impossible to allocate responsibility. Yeah, and I just list some examples there that, yeah, it could be compared to river basin case, and it could be in legal cases where you have a harm done in one country. This was an example from Canada to US, I think, where in the 40s they had to make a settlement. But whereas when you have a lot of complex moisture exchange, you would be more comparable to something like the UNESC Convention on long-range transboundary air pollution. Another aspect I just want to throw in there is also that seasonality also changes. So it's all the figures are based on mean annual, but of course you have differences between dry season and dry years. And so, for example, if we look at how Brazil share benefit from Amazon rainforest precipitation, it falls in dry season from 45 to 33, whereas Colombia increase. So it poses a question: when do you need the rainfall? When do you want the rainfall? When is the rainfall important to you? And so it also that's another aspect to consider for governance and for thinking of responsibility. And finally, I just want to very briefly mention that most recycling is something that we could consider for planetary boundaries framework. That is a framework that was introduced in 2009 first, and then received considerable uptake for everything from SDGs, from considering donut economy. So it has a lot of influence. But the current planetary boundary for freshwater use is just considering the blue water. It's actually it's actually just a proxy variable, but many have taken it as the planetary boundary. And so we were a group of people, I think a lot of, Sam is here, Fernando is here, who wanted to really look at all water cycle modifications. So I go a little bit quicker. And so if we look at all interactions between different water stores, soil moisture, atmospheric water, frozen water, groundwater, surface water, and how that interacts with the whole earth system, it's really different from just looking at just freshwater use. And so when we, in this paper, it's just submitted, so it's not published yet, but we proposed a set of, 6 sub-boundaries, and 2 of them were related to atmospheric water. And the area with evaporation change, that would be the control variable and how it changes the climate patterns. That could be a unit of analysis, say precipitation shed. So it'll be one way as well to consider to feedback to policy and governance processes. So just to summarize, I think talked about multi-cycling is important as a connector of remote land use change with local food and water security. It's transboundary in nature and connects land use and water across both basins and nations. It's a feedback mechanism between land and atmosphere with potential for self-amplification effects. It's also a valuable ecosystem service. And it's a common in need of governance and also attractive for governance because it's simple to establish causality, and it's easy to understand. But there's also a lot of challenges. So, for example, what to consider for quantification and when attributing harm. Should you take natural variability? How do you account for that in terms of precipitation that's so variable? How do you establish a baseline under climate change? What kind of spatial and temporal scale would you consider? And what is the scope analysis, and what are the beneficial? Would you think for agriculture? Would you think for ecosystems, local livelihood? And also what to consider when you are not able to quantify and attribute harm. Maybe it's actually the narrative, the norms that are more important, and maybe just apply ethical principles that are commonly accepted, like do no harm, equally sharing principles. So I think, based on this, that multi-cycling governance should consider how the desirability of multi-cycling outcomes aligns with land use change outcome. So for example, if we just consider multi-cycling, maybe plantations and irrigation is great, but that has a trade-off in terms of the local water resources, and also evaporation for precipitation versus water availability in rivers. So when you evaporate more, you get less in your local rivers. And also the balance between local livelihoods against remote stakeholders. You could get into situations when it could be a geopolitical, very hypothetical situation, like if China says, oh, we get a lot of irrigation water from India, great, let's invest more in groundwater pumping and deplete the resources of India, right? So this is also a geopolitical and power tension to consider. And how to balance scientific representativity and the practical usefulness, because multi-cycling is also just one of many land atmosphere processes. If you do too many changes, you change the circulation, and at very local scale, you also could also increase turbulence and increase rainfall rather than reduce it. So how do, as Ostrom, citing Ostrom, that should really emphasize that we should really try to understand the complexity of the system behavior that we want to govern. So with that, I think I'm actually wending over a question to you, because I'm sure that you have much more experience in your field about how the challenges that you face in science policy interface. Yeah, thank you.
Okay, thank you, Lan, for such a very inspiring presentation. And now I would like to see if somebody here has some questions for Lan. Sarah?
Thank you so much. It was very interesting to listen to what you guys have done, and inspiring as well. So regarding the moisture recycling, so has this component has been included in the global, GCMs or not yet? Or, I mean, could you please just...
Yes. So I think there are inbuilt moisture tracking in lot of, I think even in EC Earth, there's a Lagrangian moisture tracking, but because of the computational, you don't really do it for global scale. And I know that so Ruud van der End is now working with people who are integrating this moisture tracking model with EC Earth, I think. So there's more coming, and I think that will be really useful. And one thing is also that many GCMs, the climate model simulations, what I understand is also that there's a lot of ensemble runs, right? So the precipitation change is not coming out as clear, but it's important to consider those and how and also how the circulation changes could be one way to help that diagnosis as well, I think.
Another question. So if we can go back, I don't know. I mean, it was a slide about China. It was a watershed in China and India.
Early, I guess, the India, the Yangtze Basin.
You were saying that the different colors.
This one?
Exactly, this one. So what is the time span here? I mean, when we see such an impact, I mean, the changes in the flow and the moisture flow. So, I mean, what is the time span?
Right. So the land use change scenario in itself that we used was between potential and current land. So the current land, I think I used the Ramankuti data from 2007-ish, 8 maybe. And so it's that's hypothetical land use change. So that doesn't really have a time dimension in that sense. So it's just sort of trying to quantify the human impact. But then the meteorological data that we used for forcing it, this is the average over a period of 10, 15 years, I think between 2000 and 2013, I think, so 14 years.
This is average changes through 15 years of.
Yeah.
Okay.
Yeah.
Thank you so much.
Yeah, thank you so much.
Okay, thank you. Any more questions? What's your name, sir?
Gabriele Messori. So I'm partly at the Department of Meteorology here, partly at Department of Earth Sciences in Uppsala. So I was wondering, I didn't quite catch the methodology of this study here in terms of how you dealt with combining the meteorological forcing and land use change if your model isn't integrated with the GCM yet.
Right. So it's a very simple, I think I included it towards the end. I didn't talk about, right here. I knew the question would come. But so this is a 2-column of the mostly tracking model. And then we have a hydrological model down here, very small, but it's has a store for interception, a store for soil moisture, a store for transpiration, roots of storage. And then the evaporate. So this model is translating what happens when you change land to what changes you see in evaporation. And then we feed that evaporation output to the moisture tracking model. So the moisture tracking model is forced by specific humidity, winds, precipitation, and evaporation. So we replace the evaporation from reanalysis from ERA interim with this model evaporation. And so, and we start with 2 scenarios. Here it's called, so STEAM is a hydrological model. So curve will be the current land and pot will be the potential vegetation case. And we use the current day precipitation for both scenarios because we don't have a potential vegetation. So that's what we're trying to figure out, what is the potential precipitation. And we get different evaporation output from the model. And then both are fed into RAM2 layers, that's a moisture tracking model. And then it gets how much precipitation comes from land. So here we set the sink region as all continental land. So the T is terrestrial. So all terrestrial precipitation for current and for potential in the first iteration. And there will be a difference between the precipitation from both scenarios. That's the delta P, 1 for the first iteration. And we change the current precipitation by that difference in a second run, because we assume that whatever precipitation, how do you still follow? Or it's, so the precipitation change that is happening over land will have to be adjusted because that's a new potential land. But because we know that evaporation can change when precipitation changes, we have to run it again. So this time with this adjusted precipitation, we feed that into STEAM, the hydrological model, and get a slightly different evaporation output, which gives then again a slightly different tracked terrestrial precipitation with terrestrial sources, which generates another difference. And this difference is becoming smaller and smaller as the models sort of stabilizes. So that's how we needed 4 runs for the difference between potential and current land, but could of course differ. And we just had a criteria, something like if the precipitation change is less than 1% per year, 5 millimeter per month, then it's sufficiently small that we don't care about it anymore. So that's a methodology we used. A different method could be to directly have it in a coupled complex model and then do the moisture tracking within that model. So.
Okay, thank you. Any more questions?
Thanks, and really interesting, a lot of work. I'm just wondering, the first server page you show the map, the area of the sink and the area as the source, they have a lot of overlap. So I'm thinking, is it possible like one area, the land use change will affect another area, but that area also can affect another area, like cause the chain effect?
Yes, definitely.
So does the model can track this?
So the model cannot, so as soon as the precipitation falls to land, we lose track of that. So we don't know exactly the pathways anymore. So we don't know, for example, how much of that, so because it's only tracking the atmospheric column, so you can only track when evaporation enters from that moment on, and then until it falls to land. And then after it falls to land, we don't know what happens, if it's dwelling in land for a long time or if it's just interception. We can't know the entire cascade for sure, but it's possible to see the cascade effect nevertheless by doing, say, multiple tracking, and you could also derive it from more scenario analysis. And I think, yeah, I think I've seen others. I've seen other studies where they have looked at precisely how many times does it evaporate and precipitate over land. I think there was a paper, not from our group, but they had called it that they found out that it was a Poisson process, whatever that means for this context.
Thank you.
Any more questions? Yeah,
Sure. Final quick one. So I guess your two split column model conserves water, right?
So we conserve the water, but ERA interim
Yeah, I was going to say, I mean,
reanalysis
they don't
does
conserve
not.
mass and they don't conserve water.
Right.
So are you
So-
trying to conserve water and assist using data that doesn't conserve?
Yeah, so that's a slight problem that we have, is that we do have something called a loss. So we have this precipitation evaporation, we have the moisture flag, and then we have a loss term. The loss term is usually quite small, and it's not important at a longer time scale. So it doesn't affect the results or conclusions very much, but it's there because of the non-closure. Yeah, so for the seasonal analysis, it could matter a little bit in terms, especially if you look at short periods. I think we also have an ongoing study with heat waves, and then it becomes really short, and then it becomes a term that needs to be quantified. But yeah, maybe even for seasonal, but I think the seasonal ones I was showing you is also the average over several seasons, and then it becomes slightly less important because the losses sort of evens each other out a little bit, I think.
Okay, any more questions? I have two questions if there's no more questions. The first one, okay, this is all based on modeling, right? But have you been able to see if already there has been cases of moisture depletion, moisture recycling depletion now from observations, or countries that have started noticing something, reductions in precipitation that can be attributed
Yeah.
to other countries?
So there's the issue of observational issues. There's several ways of measuring, or more measurement observation. One is the isotope that I just mentioned briefly. And one issue with that is that it's also quite difficult, and there's a lot of uncertainties in that. We've been contacted by isotope people to evaluate their isotope studies with the modeling. So it's like, can we evaluate each other rather than can we just use any of that as truth? The other is that just observing the precipitation trend doesn't really help, because there are so many different, it's quite difficult to attribute. Is that because of climate change, because of circulation change, because of some natural variability, because of land use change? So I think we have seen regions where there's been deforestation, but then still increase in rainfall. So it doesn't really come out as clear results. I haven't done any of that analysis myself, but from what I read. But there's one really nice observational study from satellite-based data. It's Spracklen et al. In Nature, I think, 2000. Don't remember, 2012. I think, so what they did was to look at, so they used this Lagrangian model, moisture tracking model, and look at the particle flows and the trajectory over 10 or 15 days or something. And along this moisture flow trajectory, they accumulated the LAI. So they could establish a clear relationship between the leaf area index and the moisture increase. So they could see that the air was catching up moisture as it moved. So that was, I think, maybe the closest observational based analysis that I have seen.
Okay,
Yeah.
thank you. And then the second question was, we always relate then moisture recycling to deforestation. So there's a decrease in evapotranspiration that will imply a decrease in precipitation in another region and decreasing the amount of water availability. But let's say in cases like Sweden or China, where afforestation now is greening like the surface. So then the opposite would happen, right? So you would get more vegetation, less water on the rivers, and more moisture to move to other countries. So have you also considered that positive way of thinking of moisture recycling for governance?
Yeah, so we haven't looked at that explicitly, but I definitely think that it's useful to think of not moisture recycling as a solution in itself, but really think of the pros and cons, the synergies and trade-offs, and the risk and opportunities, and really in adjacent to all other aspects for that system. But it's interesting that you also mentioned the afforestation aspect, because that's something really happening, and also in terms of cost. Maybe some of you know the South to North Water Transfer Project. The flow that we record going from southern to northern, that goes into Yangtze Basin. I think the order magnitude, now I don't have the exact numbers in my head, but the order magnitude is very similar to what this huge infrastructure, the largest, I think, largest, most costly civil engineering project in the world is. So we should really have that in mind as well. Like, that's billions, right? So.
Okay, that was it. Thank you very much. We were supposed to have a coffee. I don't know if it has arrived, but then I would also invite you to the next seminar that we're actually having now at 2:30. There's a Professor Joshua Schimmel from University of California. We'll talk on the subject of how to write scientific proposals and papers. So if you're around, well, you're invited also. So thanks again, and thanks, Lan.
Thank you so much.
And thank
Thank you.
all of you.